My name is Cesario Tavares. I'm a PhD candidate at Texas A&M University, and I'm working with Dr. Zachary Graisley. And it's a pleasure to be here to share some of the work we're doing on machine learning to optimize mixture proportioning and performance of ultra-high performance concrete. So the topic that I want to discuss today is the development of performance density diagrams that were developed with machine learning models to optimize mixture design towards developing sustainable UHPC concrete. So whenever we're talking about UHPC concrete for people in the general public or even in the concrete industry that are not very familiar, the first question that comes to mind is the emissions, the potential source for CO2 emissions, given that this material has typically a higher cement content per unit volume. So considering that the cement emissions right now is a problem, this has led a lot of skepticism regarding the misassociation of the application of UHPC with a high potential source for CO2 emissions. Similar thing happens with the cost. The higher cost per unit volume of UHPC compared to traditional concrete is still a source of hesitancy between some designers and project owners, inhibiting them from fully embracing this technology where the application makes sense, despite structural elements being geometrically more efficient when cast with UHPC, given that they require less volume of material and they have higher durability. So the key to answer all of these questions and to lead with these misconceptions is primarily on the mixed design optimization, and also on developing tools that allow us to have an overall visualization of the trade-off that we can get between the performance, the cost, and the emissions. So the strategy developed in this study was to use a strategic experimental framework for data collection using orthogonal array designs from the Taguchi method. This will allow us to reduce the experimental runs and collect very strategic data to evaluate the material behavior. We are also using machine learning models, different models in the k-nearest neighbors and random forest to model the material response. And at the end, we will create an ensemble model, which is a very popular technique nowadays to benefit from the best features from the different models, because each model operates in a different way and they have advantages and disadvantages. And the ensemble helps us get the best out of each. Finally, the main goal of this project is to develop or to show the methodology of developing performance density diagrams and emission density diagrams that will allow us to optimize for compressive strength and environmental impact. So regarding the experimental framework, we used a orthogonal array of level 25, and the maximum contents of supplemental cementitious materials evaluated was based on the numerous considerations in the literature. We divided the study in two phases. Phase A, where we are evaluating the binder and we're trying to optimize the binder. And then we have a phase B, where we incorporate aggregates and we try to improve the microstructure, the stability, and also the sustainability of the material we're creating. Because there's no point of just making it very strong. It has to be reasonably applicable to the field. So as we gathered our models, KNN and random forest models, we were able to create this ensemble model and generate our performance density diagram. And these diagrams are faceted counterplots that allow us to evaluate multiple variables at the same time, with contrast to what we usually do with just regular 2D plots. It's also very easy to estimate the quantities of each variable that we are evaluating comparing to 3D plots, because 3D plots are very helpful in looking at the material behavior, but it's very hard to estimate magnitudes. So the performance density diagram, here you can see as an example, we faceted by fly ash content because it was the variable in our model that had the least importance when it comes to material response or the variability of the data. And we evaluated several points to see how sensitive these diagrams can allow us to estimate the compressive strength. And most of the mixtures that we evaluated, the behavior and the ranks followed our diagrams. So it has shown to be a very helpful tool for that. These diagrams, as you can also see from here, they can also be used to create multi-objective, to evaluate multi-objective indices, right? So that's another huge advantage for us. So if you want to look at what type of supplemental cementitious materials you want to use and evaluate their cost and their durability at the same time with the mechanical performance, you can do all of that in one single diagram, depending on what weights you give to your multi-objective index. And that obviously will depend from project to project and from producer to producer, right? Another great feature from these diagrams is that it can readily give you some alternatives to account for construction in different regions or to account for material shortage. You don't have to run huge or very exhausting experimental campaigns if you don't have one of the materials. So you can have a very good starting point when you're about to use that. And also if you want to explore new materials. So this is the big advantage of these diagrams also with respect to the existing softwares, because it's very good to have data sharing, and that's going to get us closer to more accurate predictive models. But in terms of developing new material, it's better to have a methodology that allows you to explore your materials in your own region and see what the impact they have on the performance. So as you can see here in the next slide, this was the second phase of our optimization study, and where we incorporated aggregates. We used the concrete sand. We used, sorry, I forgot to mention, previously we evaluated mixtures with slag, microsilica, and fly ash. And we picked one of the binders that had less fly ash content, given the less availability of fly ash nowadays. And we used that for our second phase as the binder. And in the second phase, we evaluated a natural concrete sand, a crushed sand, and also ground quartz, so the incorporation of ground quartz. And what we were able to achieve was, looking at the sustainable part, if you look at the mixture C3, we specifically picked that on this graph because it has fine aggregate to cementitious ratio over 1, which typically, if we look at what's available on the literature, this value is usually around 0.9 at maximum. So we're talking about a very sustainable material here, or at least a methodology that will allow us to get to more sustainable concretes. We were also able to achieve 155 megapascals with this admixture. And the impressive part about this is that we didn't use the best binder from phase A, because we were developing the models as we were going through the experimental phases. So the very first models were not the optimum ones. So we didn't use any special heat treatment or post-thermal treatment. We didn't use high strength cement. We used regular type 1 and 2 OPC. We didn't use fibers, which we also know that usually gives us some bump in the compressive strength for UHPC type of materials. We didn't seek precisely any dense gradation of the aggregates, so we let the model itself figure it out. We didn't use air detrainers to reduce the porosity, and we also didn't use nanomaterials, which we know are the ones that has been taking UHPC to new levels. So there's a lot of room for improvement for the already very good mixture that we obtain in this study. There is also other
4 minutes, Cesario, please.
4?
3 minutes. 3
Okay,
minutes.
thank you. Thank you. So there are other applications also that we can use with performance density diagrams, and that is with categorical prediction. And there is new opportunities we can pursue with performance density diagrams if we're looking at, for example, distress prediction or even failure modes. So just to give an example of how this can use, we used the information of the fracture type, which is not very important for compressive strength purposes, but it allows us to show how we can use this for a categorical prediction. And if we don't want to just use the prediction for each fracture type, we can look at the probability, which is a better metric to assess the probability of a distress of or a failure mode to occur. So now our next step is to take this methodology of the performance density diagrams to develop emission density diagrams, where I think it's going to be a game-changing methodology. And the best impact of these diagrams will be here, because as we know in traditional, currently the environmental product declarations, the global warming potential is reported as a unit of emission per cubic meter. But again, UHPC is more efficient, so this is not a good metric to actually assess how this material is, if it's sustainable or not. So we need metrics that account for mechanical performance. So this would be great to incorporate, and we are evaluating ways to assess different material properties to incorporate this. So as the final conclusions from the point we are now at this project is that this methodology to develop performance density diagrams will allow UHPC producers to create their own performance portrait for their own local materials and their own mixing procedures that will allow them to make a better assessment of the trade-off between performance, cost, and emissions. This methodology should definitely be extended to emission density diagrams, and it's applicable to all types of concrete, not just UHPC concrete. This will allow us to have more accurate and transparent display of environmental impact, which will bring more confidence from the general public on using these advanced materials, using a metric that accounts for the mechanical properties on the design and on the emissions evaluation. Again, this will give us more flexibility on the mixed design process, which will lead to better decision making. And also the new test protocols developed in this study and this methodology can help us explore new materials and keep leading concrete to new heights that we haven't reached yet. So I would like to thank you all for listening to me, and I'm happy to answer any questions that you might have.